Hello, Professor Kaku. Hello. Please tell me about 4 fundamental forces of nature. Why not? Look at my computer, I will explain to you. In physics, the fundamental interactions, also known as fundamental forces. There are 4 fundamental interactions known to exist: the gravitational and electromagnetic interactions, which produce significant long-range forces whose effects can be seen directly in everyday life, and the strong and weak interactions, which produce forces at minuscule, subatomic distances and govern nuclear interactions. Some scientists speculate that a 5th force might exist, but if so, it is not widely accepted nor proven. Gravitation is by far the weakest of the 4 interactions at the atomic scale, where electromagnetic interactions dominate. But the idea that the weakness of gravity can easily be demonstrated by suspending a pin using a simple magnet, such as a refrigerator magnet, is fundamentally flawed. The only reason the magnet is able to hold the pin against the gravitational pull of the entire Earth is due to its relative proximity. There is clearly a short distance of separation between magnet and pin where a breaking point is reached, and due to the large mass of Earth this distance is disappointingly small. Thus gravitation is very important for macroscopic objects and over macroscopic distances for the following reasons. Gravitation is the only interaction that acts on all particles having mass, energy and/or momentum, has an infinite range, like electromagnetism, but unlike strong and weak interaction, citation needed, cannot be absorbed, transformed, or shielded against, always attracts and never repels. Electroweak interaction, electromagnetism and weak interaction appear to be very different at everyday low energies. They can be modeled using 2 different theories. However, above unification energy, on the order of 100 GeV, they would merge into a single electroweak force. Electroweak theory is very important for modern cosmology, particularly on how the universe evolved. This is because shortly after the Big Bang, the temperature was approximately above 1015 K. Electromagnetic force and weak force were merged into a combined electroweak force. For contributions to the unification of the weak and electromagnetic interaction between elementary particles, Abdus Salam, Sheldon Glashow and Steven Weinberg were awarded the Nobel Prize in Physics in 1979. Electromagnetism is a force that acts between electrically charged particles. This phenomenon includes the electrostatic force acting between charged particles at rest, and the combined effect of electric and magnetic forces acting between charged particles moving relative to each other. Electromagnetism is infinite range like gravity, but vastly stronger, and therefore describes a number of macroscopic phenomena of everyday experience such as friction, rainbows, lightning, and all human-made devices using electric current, such as television, lasers, and computers. Electromagnetism fundamentally determines all macroscopic, and many atomic levels, properties of the chemical elements, including all chemical bonding. Weak interaction. The weak interaction, or weak nuclear force, is responsible for some nuclear phenomena such as beta decay. Electromagnetism and the weak force are now understood to be 2 aspects of a unified electroweak interaction. This discovery was the first step toward the unified theory known as the Standard Model. In the theory of the electroweak interaction, the carriers of the weak force are the massive gauge bosons called the W and Z bosons. The weak interaction is the only known interaction which does not conserve parity. It is left-right asymmetric. The weak interaction even violates CP symmetry, but does conserve CPT. Strong interaction. The strong interaction, or strong nuclear force, is the most complicated interaction, mainly because of the way it varies with distance. At distances greater than 10 femtometers, the strong force is practically unobservable. Moreover, it holds only inside the atomic nucleus. After the nucleus was discovered in 1908, it was clear that a new force, today known as the nuclear force, was needed to overcome the electrostatic repulsion, a manifestation of electromagnetism, of the positively charged protons. Otherwise, the nucleus could not exist. Moreover, the force had to be strong enough to squeeze the protons into a volume that is about 10-15 meters, much smaller than that of the entire atom. From the short range of this force, Hideki Ikawa predicted that it was associated with a massive particle, whose mass is approximately 100 MeV. I think you fully understand. Thanks, Professor.